Hello everyone, I'm Alka Janged from IIT Kanpur. I'm your TA for Nature and Properties of Materials. So today's topic is polymers. This course is offered by Professor Vishak Bhattacharya from Department of Mechanical Engineering, IIT Kanpur. So firstly we'll be going through some sample assignment questions and then we'll be going through some lecture slides. So first question is, which of the following types of the molecular structure present in the thermosetting polymers? And options are linear polymer, branched polymer, cross-linked polymer, or network polymer. So answer will be cross-linked polymer, because in case of thermosetting polymers, these are highly cross-linked, and these are in case of thermosetting polymer, these are often called thermoset, and these are obtained by irreversible hardening or curing of a soft solid or viscous liquid pre-polymer, which is also known as resin. Okay, so this is what your structures of thermosets and thermoplastics look like. In case of thermoplastics, these are linear, there will be linear chains of polymers, and these will be forming thermoplastics. In case of thermosets, they will be highly cross-linked. So this cross-links, they make them thermoset. So when we heat them again, they won't be changing their shape such as thermosets. Like we can weld these by heating easily in case of thermoplastics. Now next question is, which of the following is an example of thermoplastic material? And your examples are camera bodies, electric insulation, I think it should be electric insulations, and electric plugs and automobile parts. So one property that we know about thermoplastic, that these are flexible compared to thermosets. So we can compare that property and get one answer from this. So answer will be electrical installation. So in case of camera bodies, electric plugs, automobile parts, these all are very rigid in nature. So these all must be made using thermosets. So here we can explain, like bakelite and other resins, which are thermosets. These are used for making electrical plugs. And automobile parts and camera bodies also need to be very rigid and high temperature sustaining. So these are made of thermosets. Now next question is, which of the following is used to manufacture carrier bags? And your examples are low density polyethylene, high density polyethylene, polycarbonate, and PVC. So answer will be first. So we can explain this by saying that the first grade of polyethylene ever made, low density polyethylene or LDPE, is a versatile polymer widely used in making these carrier bags. While high density polyethylene, it is used in making advanced materials such as fuel tanks for several type of automobiles and pipes for distribute natural gases. And PVC is used for making cable insulation, pipes, and windshields. Polycarbonates, on the other hand, are used in making lenses and safety glasses. Next question is chain polymerization mechanism may occur due to, and examples are free radical, cationic, anionic, or all of the above. So your answer will be all of these. So we can explain this by saying that free radical polymerization is a type of chain growth polymerization along with anionic, cationic and coordination polymerization. So these are various types. And in case of free radical polymerization is a polymerization approach by which successive addition of free radicals takes place to form a polymer unit. So these all will be answer. Now this is a numerical. So find the degree of polymerization of a polytetrafluoroethylene polymer which has number average molecular weight of 10,000 gram per mole and it has a similar structure like polyethylene. So in case of polyethylene we'll be having 4 hydrogen atoms. So instead of that we'll be having fluoride ions, fluorides. So answer we can see how we'll be getting it. So degree of polymerization is given as formula. So number average molecular weight Mn divided by M, and M here is repeat unit molecular weight. Our repeat unit is polytetrafluoroethylene, so it will be C2F4. So we can get its molecular weight by using carbon and fluorine. So fluorine will be having 19, so we'll be multiplying it with 4, and carbon is 12, so 12 multiplied by 2, so 100 gram per mole. Now for degree of polymerization we'll be dividing this whole molecular weight divided average molecular weight divided by 1 unit's molecular weight. So we'll be getting degree of polymerization 100. So we are taking around 100 units of this tetrafluoroethylene, then we are able to make this polymer here in this case. Now 6th question is durometer is used to measure. Your options are ductility of rubber, creep of polymer, toughness of rubber, or hardness of rubber. So answer will be hardness. So this is what your durometer looks like, and this durometer or shore durometer, it is also called this, and is a standardized way to measure the hardness of materials like rubber and plastics. And durometer measurement scales range from 0 to 100, but there is no such thing as durometer unit of measurement. So this is mainly used for rubbers and plastics. Now question number 7. So it is another numerical. So in this we have to find out number average molecular weight and weighted average molecular weight for a equimolar mixture of dodecane and octadecane. So your options are 140, 145, 160, 164, 212, 220, 180, 183. Answer. So we can solve this by saying that firstly we need to find out the molecular weights of both of these, dodecane and octadecane, which is 170 and 254. So firstly number average molecular weight, it can be given as will be multiplying this mi, it is the molecular weight, and n is number of moles. So number of moles that we have to particular unit, we need to multiply it with its molecular weight. So, and then we need to add all the number of molecules and divide it. So first is dodecane. So for dodecane we need to multiply its molecular weight multiplied by 1. So here that it is equimolar mixture. So we are taking 1 mole of dodecane and 1 mole of octadecane. So both of these 1 mole, and then we'll be adding these moles. So it will be divided by 2, and 170 and 254. So the total will be 212.41. This will be your number average molecular weight. And in case of your weighted average molecular weight, here this m will be squared, and below will be adding this molecular weight multiplied by number of moles. So here 170 will be squared and 254 will also be squared, and below we need to add these. So we'll be getting 220.74. So your option C will be correct. You need to just remember these formulas mainly. Now weight average molecular weight can be determined by. So these are various techniques that we use, but which technique gives us weight average molecular weight of a polymer? Options are osmometry, abeliometry, end group analysis, or light scattering. And the answer will be light scattering, and it can be explained here that incident light, these macromolecules, they depending on their weight, they scatter the light. So this is used in this light scattering mechanism. So in case of gel permeation chromatography, osmometry, light scattering, viscometry, these are various techniques that can be used to determine molecular weight. And the addition of light scattering detection, it allows measurement of the true or absolute molecular weight of macromolecules as opposed to the relative value obtained from a conventional column calibration techniques. Moreover, light scattering can also provide the size and conformation of macromolecules without any assumption on shape. Now question 9th. The biodegradable polymer among the following is. So we know that most of the polymers are not biodegradable, and they are causing some issues to the environment. So out of these, which one is biodegradable? And options are polylactic acid, polystyrene, polypropylene, polybutylene terephthalate. And answer will be polylactic acid. And now out of these four, only polylactic acid is biodegradable, and the majority of common plastics including polyethylene, polypropylene, polystyrene, PVC and polyethylene terephthalate are not biodegradable, and these endangers the environment. And polyester, known as polylactic acid, is produced from renewable feedstock and is both biodegradable and recyclable. And fermentation of glucose or sucrose results in production of lactic acid, which is then highly purified as a raw substance. Question number 3. So a styrene butadiene random copolymer, and we'll be reading about copolymers, but here it is a numerical based on that. So with an equal weight fraction, so both have like 0.5 weight fraction. If we are taking total is 1. Okay, so of polystyrene has glass transition temperature 100 degrees C, and polybutadiene, it has glass transition temperature minus 100 degrees C. Now it shows a single transition peak. So the glass transition temperature of the copolymer is, options are minus 37 degrees C, minus 20 degrees C, minus 47 degrees C, or minus 50 degrees C. Answer is minus 37 degrees C. Now explanation can be given as this. So formula will be like 1 upon Tg equal to weighted fraction of one out of these copolymers. One monomer that is there is polystyrene, and another monomer is this butadiene. So butadiene's weight fraction and this polystyrene, its weighted fraction, divided by their respective Tg, glass transition temperatures, we need to keep. So, and T1 and T2 should be taken in Kelvin. So fraction, as I already said, these will be 0.5, 0.5, because these are equal weight fraction. And now I have converted these Tg into Kelvin. Now after calculating, it will be 0.0042. So we'll be taking inverse of for getting Tg, it will be 236.54 Kelvin. And this, then we can get this Tg, we need to get in degree C. So when we'll be converting it, it will be around minus 36.6 degrees C, which is nearest to the minus 37.0 degrees C. Okay, so now I'll be going through some lecture slides. Okay, so firstly, classification of polymers. So polymers can be classified on various bases. First one is based on molecular structure. So it can be linear, branched, cross-linked, network, and based on origin, it can be natural or synthetic. And based on polymerization reaction, it can be chain polymerization, step polymerization, and based on thermophysical behavior, it can be thermoplastic or thermosets based on advanced polymers. So their uses are relatively new. So these are liquid crystal polymers and ultra high molecular weight polyethylene, and based on the end use of applications. So based on that, polymers are also divided into such as plastics, elastomers, fibers, coatings, adhesives, films, and foams. Now, polymer classification based on origin. So a polymer is a large molecule composed of many repeated subunits. And here poly means many and mer is for parts or units. So it is made by many units. Now these can be natural polymers or synthetic polymers. And examples of natural polymers are cotton, silk, natural rubber, proteins, cellulose, starch, bone, leather. These all are organic polymers. Now synthetic polymers are synthetic rubber, bakelite, neoprene, nylon, polystyrene, polyethylene, and PVC. Now these are some polymers and their products. So forks, these tires, rubbers, These plastic bottles, helmets, these all are made using polymers. Now classification based on molecular structure. So first is linear polymers. In this case, your units are joined together end to end in a single chains. So this is how your structure will look like, and it may be some weak van der Waals bonding and hydrogen bonding between the chains. So this chain, along this chain, these atoms are bonded by covalent bonding, but between these chains they will be having these secondary bonding, which can be either van der Waals bonding or hydrogen bonding, and these are soluble and fusible. And the examples are high density polyethylene, PVC, polystyrene, nylon, polymethyl methacrylate, etc. And now second is branched. So here we'll be having some branches in other direction than primary chain. So side branch chains are connected to the main ones, and these are more soluble and fusible. An example is low density polyethylene. So this structure will be open compared to this, because here these chains can be easily aligned and filled space with high density and high efficiency. Compared to this, it will be an open structure. So this is low density polyethylene, and it high density will be in case of linear structure. Third is cross-linked polymers. In this, adjacent linear chains are joined one to another at various positions by covalent bonds, and these are insoluble and infusible. And network polymers, these are highly cross-linking and 3D network, and these are also insoluble and infusible, and examples are rubber, polyurethanes, and phenol formaldehyde. Now classification based on thermophysical properties. So these are mainly two classes: thermoplastics and thermosets. In case of thermoplastics, these are heat sensitive, and these soften and flow upon heating, and these remain soluble and fusible under many cycles of heating and cooling. Thus these can be easily recycled, and most linear polymers and those having some branches with flexible chains are thermoplastics, and individual polymer molecules are held together by weak secondary forces such as van der Waals forces, hydrogen bonds, and dipole-dipole interactions. Now these are easy to repair by welding, because will be like heating, then these can be easily welded and by using either solvent bonding. And unlimited shelf life, these won't undergo polymerization during storage or in processing unit. Now these have a disadvantage of creep, so they are highly prone to creep, so we can't use these materials at higher temperatures. Now example of thermoplastics are polyethylene, polystyrene, polyethylene terephthalate, polyvinyl chloride, nylon, PP, and poly PMMA, etc. Second is thermosets. Now thermosetting polymers are network polymers. So because of this highly cross-linking structure, these can't be reheated and made into different shapes. So these are creep resistant and less sensitive to temperature, and these attain permanent hardness due to cross linking, and then do not soften and flow upon heating. And these are also non post formable. So these are obtained in a soluble or fusible stage in the early or intermediate stage, and but once they get cured, they will be infusible and insoluble. These are excellent thermal and chemically stable once polymerized, and one of the disadvantages is that these are brittle and also non-recyclable. So if they gets broken once, so we can't use it again. Example is bakelite, epoxy, urethane, etc. Now curing of thermosets. Curing is process to transform thermostatic resin, this soft part, to the or viscous state into a infusible insoluble polymer network, which will be our last product, and under heat and pressure. So viscosity of system rises until gelation occurs. So at this point, two phases exist, a gel phase and a sol phase. So the gel phase is the gelled part, and the sol phase can be extracted within solvents. So the amount of sol phase present decreases as the reaction progresses further. Now, upon further reaction, vitrification or hardening occurs. So this is how reaction takes place during curing. So we are taking multiple monomers, and then form it will be initially in either liquid form or a viscous state, and then finally we'll be getting this highly cross-linked product. Now, addition polymerization reaction. So there are two type of reactions, addition and condensation polymerization reaction. So both have different principle. First is monomer units are attached one at a time in a chain like fashion to form a linear macromolecule. So it is characterized by the presence of a few active sites which react and propagate through a sea of monomers, and it is used for the synthesis of thermoplastics. So these are various steps that are involved. First is initiator decomposition. So for this polymerization we require some activation. So this activation is provided by catalyst. So this catalyst will be breaking into two radicals. Now chain initiation. Now this radical will be reacting with a monomer. Now this one monomer will be having like double bonds or something. So double bond or triple bond, then it will be breaking and it will be attaching itself to it, making this whole monomer reacting. So this monomer will further go and react with another monomer. Now this reaction will be chain propagation. Now chain will keep propagating. Now final step will be termination. Now all these monomers with this active sites, these will finally terminate. These will add up and these will terminate and will be forming a polymer. In case of condensation polymerization, it involves more than one monomer species. So there will be more than one type of monomer. So monomers can react with any nearby monomer. Now monomers can react with any nearby monomer. No special activation is needed to allow a monomer to react. Now in case of addition polymerization we required catalyst, but here we won't be requiring that. And a small molecular weight byproduct such as water or ammonia will be eliminated, which is known as like condensation. So Now typical reaction looks like this one, HOROH. R is some like alkane or some group like that. Here it will be reacting with HOOC, RCOOH. Now it will be producing S2O and forming a product. Now second step, this product will further reacting with another monomer. Now this reaction will keep going on, and finally it can be summed up and shown in this format. Now the thermosetting polyesters, phenol formaldehyde, nylons, polycarbonates are produced by condensation polymerization. Now these are mainly these polymers are condensation polymerization gives us mainly thermoset polymers, advanced polymers. Now ultra high molecular weight polyethylene. Now linear polyethylene that has extremely high molecular weight, and its trade name is Spectra or Dynama, and it is an extremely high impact resistance and outstanding resistance to wear and abrasion, has low coefficient of friction, self lubricating and non-stick surface, and a good chemical resistance to normally encountered solvents. It also performs excellent at low temperature properties and outstanding sound damping and energy absorption characteristics. Now these most of these characteristics are required in making these gears. Demerit, one of the demerit these show is mechanical properties diminish rapidly with increasing temperatures. So these are not used at higher temperatures. Liquid crystal polymer. Now aromatic polyesters based on p-hydroxybenzoic acid and related monomers, and they are in the liquid crystalline state. So these are not purely either liquid nor purely crystalline. This is a middle state, and it is considered as a new state of matter. Now these are capable of forming regions of highly ordered structure while in the liquid phase, but regularly lower than solid. Regularity is always lower than the solid crystal. Now these are extremely unreactive and inert and highly resistant to fire. So these are used in making LCD displays and on digital watches, flat panel computer monitors, televisions, and other digital displays. Now, another applications of polymers includes making films, forms. Now, in case of films, now polymeric films which will be having a thickness between 0.025 to 0.125 mm are used extensively as bags for packaging food products and other textile products. And these are other important properties of these polymeric films are that these are required to have low density. These also have high degree of flexibility. These have high tensile and tear strength, and these are resistant to moisture and other chemicals. Examples are polyethylene, polypropylene, cellophane, etc. And in case of forms, these contain a relatively high volume percentage of small pores and trapped gas bubbles. These are commonly used as cushions in automobiles and furniture, as well as in packaging and thermal insulation. Now other applications are in coatings, fibers. In case of coatings, the ingredients in coating material are usually organic polymers which are classified as paint, varnish, enamel and shellac, and these are applied to the surface of materials to protect the item from corrosive and deteriorative reactions, and these provide these also can provide electrical insulation and to improve the object's appearance. In case of fibers, these are long filaments having at least 100:1 length to diameter ratio, and these are subjected to mechanical deformations such as stretching, twisting, shearing, and abrasion. And these are widely used in the textile industry for making fabric and clothes. Another application is adhesives. Now, these are used to join large variety of materials, which can be metal, ceramics, polymers, and composites. So these their advantages is they are lighter in weight. They have ability to join even dissimilar materials and thin components. These are better. These give better fatigue resistance and lower manufacturing costs. And but they have a limitation of that they can survive high temperature. So that's why we move on for metallic welding for metals, because these polymers they can't survive higher temperatures. Now some natural adhesives are animal glue, some protein, starch, and rosin, which is found in pine tree, and some artificial adhesives are epoxy, polyurethane, and acrylic polymers, and the applications are in aerospace, automobiles, sticky notes, etc. Now another application is in making elastomers. So elastomers are mainly, these will be having this trace strand curve as this one. So amorphous polymer with viscoelasticity. Both viscosity and elasticity, these will be having very weak intermolecular forces and low Young's modulus and high failure strain compared with other materials. Now for a polymer to be an elastomer, it must not easily crystallize, and molecular chain should remain naturally coiled in the unstressed state so that we can stretch it to very high strains. And the chain bond rotation must be free to readily respond to an applied force. So as soon as we apply some force, it should be easily uncoil these chains, and they should show delayed plastic deformation. And examples are mainly some rubbers such as silicone rubber, butyl rubber, nitrile rubber, polychloroprene, and neoprene, etc. Applications are in making gasket seals, which fill the space between imperfect mating surface to prevent leakages, noise and vibration dampeners, and car door seals, etc. Plastics. Now, these are malleable and can be molded into solid objects of diverse shapes. And some plastics are very rigid and brittle, and others are flexible, so such as seen here. Now, some plastics can be as rigid as this one, which is shown here as brittle polymer, and plastic some can be tough also. Now these are used in general purpose applications and may be either thermoplastic or thermosetting in nature. Now some of the specific applications of various polymers are given here. So first is polyethylene. It is used in making toys, battery casings, bottles, carry bags, etc. And polystyrene is used in making thermal insulations, packaging consumer goods, etc. And polyester is used in making clothing, ropes, bottles, etc. Acrylics are outdoor signs, lenses, aircraft enclosure, nylon for making clothing fibers, conveyor belts, fasteners. Polypropylene is used in making syringes, petri dish, plastic furniture, and Teflon is used in making that coating which is there on non-stick pans, and Teflon tape, bearing coatings, and epoxies are used in making metal coatings and composites, adhesives, etc. Now, there are two types of molecular weights that we require in case of polymers. First is number average molecular weight. Second is weighted average molecular weight. In first, total weight of all polymer molecules in a sample are divided by the total number of polymer molecules in a sample. So here we'll be multiplying this molecular weight to the number of moles divided by entire total number of moles. Now this will be giving you number average molecular weight. In case of weighted average molecular weight, we saw its formula here. M is squared and M will be also in denominator as well. So here it's based on the fact that a bigger molecule contains more of the total mass of the polymer sample than the smaller molecules do. On degree of polymerization, and its formula is given as number average molecular weight divided by the molecular weight of the repeat unit, which is M. So it's as we increase degree of polymerization, melting temperature of a polymer keeps on increasing. So example is given here. So like suppose for polyvinyl chloride, which has this number average molecular weight as 21,150 gram per mole, and the repeat unit molecular weight we can calculate easily. It will be 62. Then for degree of polymerization we have to just divide this Mn by M, and it will be 341. So we require these many monomers of your vinyl chloride, so for getting this polymer. Now another property of polymers is polydispersity index. In this we just divide this weighted average molecular weight by number average molecular weight, and the larger the polydispersity index, the broader the molecular weight. And the monodisperse polymer, where all the chain lengths are equal, such as a protein, has a pi is equal to 1. So if the various the distribution, it just shows how the distribution of various chains looks like. If the chain lengths are all equal, then it will be 1. If there is a various small chains as well, and various chains which are very has very long chains, then polydispersity index will be higher. So step polymerization reaction typically yields values of pi equal to 2, and chain polymerization is, it can vary between 1.5 to 20. Now this is how distribution of chains and with molecular weight it will vary. Now copolymers is another term. So when there is more than one type of mer present, so like two monomers are present there, two type of monomers or more than two, then it will be called copolymer. So the molecule is a copolymer. Copolymers are a common type of material used commercially. So examples of copolymers are ABS and polyethylene vinyl acetate and nitrile rubber. Copolymerization is a method by which copolymer is created from various types of monomers, and it is frequently used to enhance or change particular characteristic of plastics. Some types of copolymers are Kraft copolymers, block copolymers, and alternating copolymers. Now, copolymer here it's similar to making composites. So, like if A and B, there are two type of monomers. So, if one monomer has certain properties and B has different type of properties, so we can get a mixture. So like Tg will be different for both of these, so we can get a particular property by combining these. And here block copolymer, in this this type of one block will be of A monomers, and other unit, this will be one block will be of different type of monomers. In random, these all will be randomized, and in alternate, AB, this type of alternating will molecules will be there. Now, physical states of polymers. Now, classification of polymer materials. These can be either partially crystalline, these can be viscoelastic, these can be highly elastic state. Examples are rubbers. It can be glassy state as well. Example is organic glasses from polystyrene, polymethyl methacrylate, polyvinyl chloride, etc. So when it is liquid, when polymer is there, so when we cool it, so it is more likely to either become totally amorphous or it will become partially crystallized. It will never become a perfect crystal, such as metals. Now, crystallinity in polymers. Now, crystalline region can be defined as orderly arrangement of molecular chains. High crystalline means higher density. If it is crystalline like here, so these chains will be aligned, so it will be having very good packing in that particular area, so it will lead to very high density, and this high density will also give it more strength because there will be good bonding between these, and it will be having high resistance to both dissolution and softening by heating. And density of crystalline polymers is higher than amorphous polymers due to close packing. Now, degree of crystallinity in polymers, it ranges from completely amorphous to about 95% crystalline, but it can never achieve 100% crystalline. In case of metal specimens, these are almost always entirely crystalline, and ceramics are either totally crystalline or totally non-crystalline. Now these are amorphous region and these are crystalline regions. This is how partially crystalline polymers looks like. There will be bunch of chunks of crystalline regions. Now, crystallinity in polymers. Now, this crystallinity, it depends on various factors. First is rate of cooling during solidification. So if we cool it very faster, then time for alignment won't be there and it will be less crystalline. It is similar to what we see in metals. Now, chain configuration. More the side branching and cross linking, more the restriction to prevent the chain alignment, and lesser will be the crystallinity. So if there is more cross linking and side branches are there and pendant atoms are there, then it will be having less crystallinity. Thus, linear polymers have high degree of crystallinity, and most network and cross-link polymers are almost totally amorphous. So, thermoplastics are more likely to show high crystallinity. Crystallinity in polymers. Examples of highly crystalline polymers are polypropylene, nylon, Kevlar, and Nomex. And examples of highly amorphous polymers are polymethyl methacrylate, polycarbonate, and polyisoprene. And percent crystallinity can also be given by using this formula. Here, rho c is density of specimen, and if we solidify this particular polymer, and density of totally amorphous polymer and density of perfectly crystalline polymer, these two are required, and then this formula can be given as percent crystallinity. Now, another property of polymers is tacticity. Now, it is different atomic configuration for the same composition. So, like these all will have same composition, same number of carbon atoms, same number of hydrogen atoms, but it will have different configuration. So, tacticity is the way pendant groups are arranged along the backbone chain. Backbone chain is this one, this all carbon atoms main chain. Pendant atoms are arranged along the backbone chain of a polymer. Now, the types are isotactic and syndiotic, which is regular geometry facilitates the fitting of adjacent chains, thus more crystalline. So these two will be showing higher crystallinity, while atactic will be randomized, so poorly crystalline due to irregularity in side groups. Also, larger the side bonded groups of atoms, lesser the tendency for crystallization. So if these bonded atoms, these pendant atoms, if these are bigger, then there will be tendency for lesser crystallization. Now, another property is glass transition temperature. The temperature at which the polymer experiences the transition from rubbery to rigid state. So below Tg, the polymer becomes hard and brittle like glass due to the reduction in the motion of large segments of molecular chains with decreasing temperature. Tg is different for each polymer, and glass transition happens only to polymers in the amorphous state. Now this is what there are various glass transition temperatures given here. So for polycarbonate, polystyrene, it is in plus, and polyethylene, which are flexible at room temperature, these will be having negative glass transition temperatures, because these are at room temperature, these are flexible, while compared to these polycarbonate, polystyrene. Now, factors which affect glass transition temperature. So chain length, Tg is proportional to the molecular weight of the polymer. So as the molecular weight increases, Tg will also increase. Chain stiffness, it increases if double bonds, aromatic groups, bulky or large side groups are present, and increase in Tg. So if chain stiffness increases, this Tg will also increases. It will come into positive degrees Celsius. Now plasticizers, addition of plasticizers reduces Tg, because plasticizers will make your polymer more tough. Cross-linking reduces chain mobility, so Tg will be increased. So your this polymer will become more brittle. Copolymers. Now Tg will be based roughly on the weight fraction of each material present in the copolymer. Effect of temperature on polymer. Now as temperature is increasing, elastic modulus will come down, and also if we are increasing crystallinity, with increasing crystallinity elastic modulus is increasing, and with also increasing cross linking your elastic modulus is increasing. Viscoelastic deformation. An amorphous polymer may behave like a either glass polymer at low temperature, or as a rubbery solid at intermediate temperature, or as a viscous liquid at very high temperatures. So for intermediate temperatures the polymer is rubbery solid viscoelastic behavior. Now fracture in polymers. So the low fracture strength compared to metals and ceramics in case of polymers. And fracture mode in thermosetting polymers is brittle because they are highly cross-linked. And in case of thermoplastic, they are both brittle and ductile are possible. And the crack will form at the region of localized stress concentration. So scratches, notches, sharp flows, these all provide some stress concentration. Now the factors which favor brittle fracture. So if we reduce temperature, or if we increase strain rate, or if we introduce some sharp notch, if we increase the specimen thickness, these all will lead to a brittle fracture. So these are similar to what we see in case of metallic specimens also. Now this trace strain behavior of various materials. So this is what the blue one is shows for elastomers, which are polyethylene, PTFE. These are soft and flexible and tough and ductile. It is for ABS and nylon. Rigid and brittle, these are for thermosets. So these are melamine, phenolic, etc. Fracture in polymers. So in case of amorphous thermoplastics, below Tg they behave as brittle, and above Tg they behave as ductile. So in case of brittle they show low fracture resistance, and above Tg they show high fracture resistance, and plastic yielding will occur prior to fracture if it is ductile. And fracture phenomena is known as crazing in case of polymers, and crazes is region of localized plastic deformation. Now it form at a highly stressed region associated with scratches, flaws and molecular inhomogeneities, and it leads to the formation of small and interconnected microvoids, which is shown here. And region between microvoids, these are known as fibrillar bridges. And under load, under load the fibrillar bridges they elongate and break, and microvoids they grow and merge. Here they will keep on merging and leading to this crack formation. Now thus the crack propagates perpendicular to the applied tensile stress. So if we are applying this tensile stress in this direction, your crack is going perpendicular in this direction. Fatigue in case of polymers. So polymers they undergo fatigue failure under cyclic loading. fatigue behavior is more sensitive to loading frequency than to metals, and high frequencies and or relatively large stresses can cause localized heating which softens the material leading to failure. So we know that heating problem will be more in case of your thermoplastics. So they will get affected by heat very rapidly, so they will show poor fatigue resistance. So these materials, these are which are lower here, these will show poor fatigue resistance compared to these one. Now factors affecting mechanical properties. First is temperature. An increase in temperature produces decrease in elastic modulus. So as we are increasing this temperature from 4 degree to 60 degree C, we are seeing that elastic modulus is decreasing, like it was higher for the 4 degree C. Reduction in tensile strength. So tensile strength is this highest point, and this is also decreasing. And enhance in ductility. So we are seeing that the strain that is there, fracture strain, it is increasing with increasing temperature. And molecular weight. So as we increase molecular weight, these mechanical properties, they are enhancing. For many polymers, tensile and impact strength increases with increasing molecular weight due to increased chain entanglements, and viscosity also increases with increasing molecular weight, and it can be shown here. Now another factor is degree of crystallinity. So higher the crystallinity, higher the close packing. So if crystallinity is there, close packing will be there, so high density will be there, and more strength, higher resistance to both dissolution and softening by heating. Cold drawing. Now it is analogous to the strain hardening in metals. So here after cold drawing, we are seeing this chains are more likely to get aligned. Now it is used to production of fibers and films, and molecular chains become highly oriented. And properties of drawn materials are anisotropic. As we can see here, these all are aligned in this direction, so strength in this direction will be different than strength in this direction. And perpendicular to the chain alignment direction, strength is reduced. So this is chain alignment direction, so in this direction your strength will deteriorate. Now this is how they have drawn your polymer, and this is how chains have aligned. Now this is all from my side. If you have any query, you can ask.
Madam,
Yes,
can you please share this material to
yes,
my
yes, I'll
address?
mail you.
Mail ID we are typing here. Madam.
Okay, okay.
Madam, are you going to end this lecture, madam?
Yeah, I have gone through the lecture slides. If you have any query, you can ask.
Uh, Please share this material, madam.
Yes, I will share you after I finish the class here. Okay. After I finish recording, after 5 o'clock, I'll send you.
We have typed the mail IDs here, madam.
Yes, I
Can
will.
we can we leave this session, madam?
This session, I'll be sharing these slides.
Madam, uh, can we leave this session, madam?
Yes, you can leave.
Mail IDs already we have
Yes,
sent,
I have
madam.
recorded.
Okay, they are leaving, madam. Thank you, madam. Thank you very
Okay.
much.
Okay. Welcome.
Madam, please send me to mail ID also, madam.
Okay, sir. Okay, I'll send you.
Jayaprakash dot
Yes, I've recorded.
Jayaprakash dot GPT,
I've
madam.
rec- I've recorded. I've recorded.
Yeah. If possible, that from first assignment itself, can you share it, madam?
Yeah, yeah. I'll send you.
If I attended first assignment also, at that time also I requested, but not received, madam. Please.
Okay, I'll send you. I thought NPTEL
Okay.
team will send you, but if you didn't receive, I'll send you today.
Okay, madam. Thank you,
Okay.
madam.
Okay.
Okay.